All right, welcome back to the second part of our lesson on electrochemical kinetics. So in this sub video, we're going to be talking about some useful kinetic relations. First off, we want to take our equation that we derived last time, which related current and potential and the concentration at our electrode surfaces. We want to see if it matches up with other electrochemical theory. We want to see if it's valid. So let's see what happens at equilibrium. If at equilibrium, our current is going to be equal to 0, and our concentrations at the surface of the electrode will be equal to the concentrations in the bulk. And so we can cancel out the current, and we can rearrange to get our concentration ratio here. Then we combine terms in the exponential term until we're left with this exponential term, where remember this little f, that's Faraday's constant divided by the universal gas constant and temperature. And then we have the difference between the equilibrium potential and the formal potential. And just again, note that this was derived specifically for one electron reactions. So when we simplify, we take the natural log of the exponential term. Then we're left with the Nernst equation after we reorganize a little bit. So very gratifying. It's a strong indication that the equation that we derived in the last video is a good and fair one, at least at equilibrium. Let's build out a few useful ideas like exchange current. So at equilibrium, it's not as if we're saying that there's no reaction happening. What we're saying is that the net reaction is in equilibrium. So the cathodic reaction and the anodic reaction, they're equal in magnitude. And what's this magnitude? We call it the exchange current. And to derive it, we just take half of our former expression. So notice this is only for the forward reaction, and we're neglecting the backwards reaction here, but we're doing it at the equilibrium potential. Well, then we need to find a way to simplify this exponential term into something that's a little bit more wieldy. And so what we do is we recall the rearranged Nernst equation. We raise both sides to the negative alpha, and that allows us to substitute in and simplify up this top expression into this lower expression for the exchange current. So you'll notice once again, there's no n in the expression because we're assuming that it is equal to 1, that there's one electron in our reaction. So what about another expression, the current over potential equation? This is a very important one. And the reason why it's so important is because it's going to allow us to move away from terms with the formal potential in them to expressions where we have the equilibrium potential inside, which just makes these expressions nice and easy to work with. How we're going to do it is we're going to take a ratio between this expression and the exchange current that we just developed. And when we do this, we're left with, a little complicated of an expression. So what we're going to do is we're just going to go through and combine terms, do some algebra until the expression is simpler. So here we've grouped together terms with like powers. So we group together these terms because they have a like power of -1 minus the transfer coefficient, and we did the same with these terms. Now we're going to use the rearranged Nernst equation raised to specific powers in order to make some substitutions. So for example, here the rearranged Nernst equation is raised to the alpha, and here it's raised to the -1 minus alpha. That allows us to do some substitutions, and then we're left with this expression where we have these exponential terms that look rather complicated, but you'll notice that we can subtract or cancel out the formal potentials in these terms because they have opposite signs. That's what we're after, and then we're only left with our potential and the equilibrium potential. So we do this, and we're left with the current over potential equation. And you'll notice that here we have eta, where eta is defined as our potential minus our equilibrium potential. So let's talk about a few special circumstances. What if we have a very well mixed solution or currents that are very low? And what will turn out in this case is that our bulk concentrations will be equal to our surface concentrations. Okay, so let's assume that this has happened. We're going to take our current over potential equation, and the concentration ratios cancel out, right? They become equal to 1. And when is this equation appropriate? Well, it's appropriate when we're about 10% or less of the limiting current. So notice the simplicity of this equation. This is one that is used very frequently in reaction kinetics, and we'll be using it to derive a few more useful relations. What happens to the Butler-Volmer equation at low overpotentials? We get the linear approximation. So if eta, or the overpotential, is small, then we know that the current will actually be small, will also be small, because the current is proportional to the exponential to e raised to the power of the overpotential. So in that case, we take our expression here, and then we say that it's very small, right? Eta is very small, which means that the whole term of x is very small, and we can approximate that as 1 plus x. So we can take this equation and approximate it at small overpotentials to be equal to this equation. Okay, so we cancel out terms with opposite signs, and what we're left with is our current at low overpotentials is equal to our exchange current times small f, where this is Faraday's constant, over the universal gas constant and temperature, and then that's multiplied by our overpotential. We can rearrange terms and define the charge transfer resistance as well. So we arrange it by putting the overpotential over current. Remember, V equals IR. And this allows us to define both of these terms. Now, what if we have large overpotentials? Well, in this case, we know that we need to be stirring. It no longer makes sense for us just to be applying low potentials, low currents. So we're stirring, we have large overpotentials. In this case, we know that either the forward or the backwards reaction is going to dominate. And so we'll just write out one of these expressions. In this case, this would be the backwards reaction. And we're going to group the current and the exchange current together. We'll take their natural log. We shift some things around, and then we linearize our expression. So here we have our overpotential as a function of current is equal to this term. And you'll notice that here, everything here is a constant, and then here, only these terms are constant. It's a straight line. So we have our intercept and our slope. So here are a few questions for you to go over. Go ahead and stop the video now and answer them. And in a few seconds, I'll give my answers to these questions. All right, welcome back. So, as you wrote out the Butler-Volmer equation, hopefully you got something that looks like this. This is just something that you practice. It could be one thing that I found very helpful for learning this is to do the derivations that I walked you through. Just do them on your own. Write them out on a piece of paper. That can be very helpful. Now, what conditions are required for the Butler-Volmer equation to hold, to be valid? Well, we derived everything assuming that the activity of electrons is equal to 1, that there's only one electron being exchanged. We assume that there's no change in pressure or volume during our reaction. And we assume that the concentration at the surface of our electrode is equal to the bulk concentration of the solution. Okay, well, we hope you'll join us next time as we talk about statistics and curve fitting.